Imagine a car that runs on gasoline and also converts another plentiful, less expensive liquid into gasoline. Even more gasoline than to start with. 12 litres produced for every 10 litres consumed. This would provide the fuel necessary to resupply the engine with enough left over to run other cars. Once the process is started, the car would only have to be supplied with the inexpensive liquid and no more gasoline is needed. Although a dream for cars, such a process can be used for certain types of nuclear reactors, the fast breeders. The gasoline of nuclear reactors is fissile material, and the product which can be converted to gasoline, fertile material. Fissile material consists of heavy nuclei which split when bombarded with neutrons and release energy plus other neutrons, allowing to maintain a chain reaction. Fertile material also consists of heavy nuclei, which although initially non-fissionable, can be converted after neutron capture and short-term disintegration into fissile nuclei. Fertile material is far more abundant than fissile material. As everyone knows, uranium is a mixture of two isotopes, uranium-235 and uranium-238. Uranium-235 is fissionable and most often used as a source of energy in nuclear power plants, but much scarcer than uranium-238, since only 0.7% is found in natural uranium. Uranium-238, on the other hand, is fertile and can be converted into fissile plutonium-239. This is the basic reaction used in breeder reactors. When fissile and fertile uranium are mixed with slightly over 15% plutonium, a chain reaction can be sustained with fast neutrons in such a way that every time 100 plutonium-239 nuclei are consumed, 120 uranium-238 nuclei are changed into plutonium-239, thus producing, as in our example of the car, more fissile material than actually consumed. In this way, the fissile material necessary to continue providing energy is reproduced while generating additional plutonium usable in other breeder reactors. Once the process is started, only uranium-238, a particularly abundant material, is consumed. Inside the cylindrical core of a breeder reactor, where the plutonium-uranium-238 mixture is located, every time 100 plutonium nuclei are consumed, only 80 are actually produced, because the core alone is not a breeder. But by placing pure fertile material around its perimeter to form what is called a blanket, the neutrons escaping from the core allow conversion of 40 additional nuclei into plutonium, resulting in the 120 nuclei typical of the breeding phenomenon. The interest of this breeding process is to use uranium-238, so much more abundant than the fissile uranium-235. Whereas usual nuclear power plants consume only uranium-235 and some uranium-238, which is converted to plutonium, the breeder reactors should allow gradual consumption of almost all the uranium-238. The gain is therefore tremendous. In comparison with light water reactors, 50 to 70 times more energy can be obtained from the same quantity of uranium ore. This is why breeder reactors are being developed. However, they have other novel features, as a description of the 1200 electric megawatt Superphénix plant at Crémalville will show. The basic arrangement of this plant differs from the one used in conventional nuclear power plants. Pressurized water reactors have a primary system in which coolant flows under pressure to convey heat released in uranium fuel rods to steam generators, where feed water in another system is converted to steam to drive a turbine generator. A third system condenses the steam discharged from the turbine. Compared with this conventional arrangement, breeder reactor design is considerably different. First, the normal fissile isotope, uranium-235, is replaced by plutonium-239. In addition, since the breeding concept requires a chain reaction employing fast neutrons, a coolant had to be selected which does not slow down neutrons, sodium. This metal, which is liquid above 100 degrees centigrade and does not have to be pressurized, is an exceptional heat conductor. However, it does also have some drawbacks. It becomes radioactive in the reactor core. It reacts violently with water. And since this may occur in a steam generator, such contact is considered an unacceptable risk. Consequently, the two main systems have to be separated by another system filled with non-radioactive sodium. There is dual heat transfer, once in an intermediate sodium-to-sodium heat exchanger, then in a steam generator. Thanks to this design feature, the consequences of any sodium-to-water contact are mitigated because no radioactivity is involved. All radioactivity is contained in the primary system, specially arranged so that the reactor and the intermediate heat exchangers are housed inside the same main containment vessel. This is the basis of the pool or integrated type design. The entire primary system is hung from a steel and concrete upper slab. First, the primary vessel, which contains the sodium, with the reactor in the center, surrounded by the intermediate heat exchangers, also suspended on the periphery. There is not one, but 8 heat exchangers which operate in parallel, while 4 pumps, one for every 2 heat exchangers, circulate the sodium. Now let's take a full-scale look at this. Imagine a huge concrete cylinder forming a shaft-like structure 24 meters in diameter. This is the location of the entire primary system. Completely hung from this steel and concrete slab, nearly 3 meters thick, and weighing over 4,000 tons unequipped. Connected to this slab is the main containment vessel designed to confine the sodium. Its diameter is 21 meters. At the bottom is a support structure and a diagrid, which resembles a flat box and is used to position the reactor core and supply it with sodium. All around these structures is the giant funnel which separates the hot sodium area at the top from the cold sodium area at the bottom. The primary sodium pumps and the intermediate heat exchangers are installed in special shafts. A total of 8 heat exchangers and 4 pumps are provided to remove the 3,000 megawatts of heat released in the core by circulating the primary sodium. The main vessel contains 3,500 tons of this sodium, which need not be pressurized because it remains well below its 900 degrees centigrade boiling point. At the hottest spot, at the core outlet, the primary sodium attains only 550 degrees centigrade, the temperature at which it reaches the intermediate heat exchangers. Here is one of the 8 heat exchangers, 18 meters high and weighing 80 tons when empty. Through the top of the upper slab from which the heat exchanger is hung, secondary sodium enters and exits. Heat transfer takes place in the body of the component, inside the tube bundle consisting of 5,400 tubes, each 6.5 meters long, welded between two circular plates. The secondary sodium arrives at 350 degrees centigrade, flows down the central column, and then up through the tubes, where it is raised to 530 degrees centigrade. Only 20 degrees centigrade less than the primary sodium, which conveys heat from the core. It is then immediately drawn into the heat exchangers, where it flows down through the tubes and emerges at the bottom at 400 degrees centigrade. Next to each intermediate heat exchanger is a pump, which immediately draws in and then discharges the sodium into two pipes, which return it to the diagrid under the core. Each pump then sends sodium to the core at the rate of 4 tons per second. The bottom section of the pump body is 2.5 meters in diameter and over 22 meters high. Combined with its electric drive motor, it extends 8 meters over the upper slab, which supports the entire weight of the pump, 150 tons. 2 intermediate heat exchangers are associated with each primary pump to provide symmetrical flow of the primary sodium. At 400 degrees centigrade in the cold collector, and 550 degrees centigrade in the hot collector at the core outlet. All of the primary sodium thus circulates in the main vessel according to this 4 times repeated system, since there are 4 primary pumps and 8 intermediate heat exchangers. This completes the description of the primary system, entirely submerged in liquid sodium and hidden beneath the upper slab inside a solid concrete enclosure. All of this system is located in the center of the reactor building, 60 meters in diameter and 80 meters high. This situates the first of the 4 main systems. The primary system, which transfers heat from the core to the intermediate heat exchangers. The next system must in turn transfer the heat received from the intermediate heat exchangers to the steam generators, which are installed around the reactor building. There are 4 steam generators, each one located in a separate building. Heat is conveyed to these steam generators from the primary system via 4 independent secondary sodium loops, each including 2 intermediate heat exchangers and a pump. Let's follow one of the secondary loops. Above the upper slab, the 2 intermediate heat exchangers on each side of the primary pump are in the same secondary loop with the associated steam generator. The hot sodium at 530 degrees centigrade is conveyed through 2 pipes to the steam generator, where it cools by converting the feed water to steam. It emerges at 350 degrees centigrade in a single pipe, which connects with a secondary sodium pump. The sodium is then discharged to the intermediate heat exchangers through 2 pipes, again with expansion loops. The 400 tons of this non-radioactive sodium contained in each secondary loop are circulated by a secondary pump built into a 5-meter diameter expansion tank. Rotation of the pump provides a flow of over 3 tons per second. The most important component in each secondary sodium loop is the steam generator. The sodium, which flows from the top downward, arrives at 530 degrees centigrade and leaves at 350 degrees centigrade after transferring heat to tubes, which are helically wrapped and arranged in layers to form a bundle around a central core. In all, there are 360 tubes, each 90 meters long. Feed water enters at the bottom of the steam generator, heats up, and vaporizes in the tubes immersed in the secondary sodium, then leaves in the form of steam at a pressure of over 180 bars and a temperature of 490 degrees centigrade. This is the function of the 4 steam generators at the end of the 4 secondary loops. Constituting the secondary or intermediate sodium system. The third system is the steam-water system. Steam from the steam generators drives the turbine generators. 2 pipes take the steam from the 4 steam generators to the turbine hall to drive 2 identical turbine generators. It is then condensed, and the water recovered is returned to the steam generators via 2 other pipes. The steam-water system is thus located outside the reactor building. The 4 steam generators, each in a separate building, are connected with the turbine hall through 2 steam feed pipes and 2 feed water return lines. The 2 turbine generators, each rated at 600 electric megawatts, are thus driven by the steam-water system, which constitutes the third system. Only the 4th system is missing, the condenser cooling system. This system uses water from a nearby river as a heat sink to condense the steam. The water taken in upstream passes under the turbine hall into the condensers and is discharged downstream at a slightly higher temperature. The plant's high efficiency, over 40%, also allows heat up of this water to be limited. This completes the description of the 4 main systems in this nuclear power plant, noteworthy primarily for the presence inside the reactor building, at the center of the main vessel, of fuel assemblies containing fissile and fertile material for the breeder reaction. The mixture of plutonium and depleted uranium comprising the Superphénix core occupies a cylindrical volume 1 meter high and 3.6 meters in diameter. This core is surrounded by a fertile blanket approximately 30 centimeters thick. The core material is a mixture of plutonium and depleted uranium oxide, while the fertile blanket consists of only depleted uranium oxide. These materials are prepared in the form of small oxide pellets, highly resistant to radiation and heat, which are stacked inside steel fuel cladding tubes so thin that they are called fuel pins. There are 100,000 pins in the central core area and 20,000 in the peripheral blanket. The core fuel pins are thinner than those in the peripheral blanket. They radiate much more heat. A steel wire is wrapped in a helical pattern around each fuel pin to provide space for sodium flow because the pins are pressed against each other inside hexagonal structures. 271 thin pins in the fissile fuel assemblies and 91 larger pins in the fertile fuel assemblies on the core periphery. During reactor operation, the primary sodium flows upward into the fuel assemblies and along the fuel pins to remove heat. 364 fissile fuel assemblies constitute the core. A total of 24 hexagonal channels are reserved for the rods which control the chain reaction. 233 fertile fuel assemblies complete the core blanket assembly, containing a total of 5 tons of plutonium and 110 tons of depleted uranium. The entirety is surrounded by steel shielding elements. This was a basic outline of the heat source used in fast breeder reactor plants. Coming after Rhapsody at Cadarache and Phénix at Marcoule, Superphénix at Crémalville served as our demonstration. This new achievement is a third key step in the development of breeder reactors. The aim is high, to obtain 50 to 70 times more energy from uranium, which amounts to multiplying all uranium reserves in the world by a factor of more than 50.